Swayam Prabha. Digital India. Educated India.
In this class, we will look at multi-parameter stress and displacement field equations. In fact, 2 classes earlier, we had discussed generalized Westergaard equations for mode 1 situation. And in the last class, we had taken up Williams eigenfunction approach. In the case of Westergaard's approach, it used complex variables, while eigenfunction approach by Williams used real functions. And what Williams considered? He considered a wedge, and he mentioned that the stress function phi could be taken as r power lambda plus 1 multiplied by f of theta. And what we did, we applied the boundary condition on the crack faces. The crack faces are free. This is depicted by the boundary conditions tau r theta equal to 0 and sigma theta equal to 0 at theta equal to plus or minus alpha. The problem becomes a crack problem when alpha becomes pi. And you should also note one more aspect. See, if you look at English solution, what he did, he solved the problem of an elliptical hole in a tension strip. His focus was only on the elliptical hole. In the limiting case, he was getting how a crack will be more dangerous from his analysis. In a similar vein, what Williams did, he actually took a wedge problem. By changing the value of alpha, you could get solution for variety of wedge angles, and when you make alpha equal to pi, it becomes a crack. So both had some similarity. In the limiting case, they consider the problem of a crack. And how the crack faces are free. This is a very important observation when you look at the Williams eigenfunction approach. We would see in the next chapter that Westergaard's generalized stress function approach can accommodate loaded crack faces. They are also very important. From an engineering analysis, you may need to find out what happens in the case of a riveted hole. So the rivet sitting there will apply a force on the crack faces. So one of the advantages of Westergaard's stress function approach is one can also study loaded crack faces. Now we will continue with Williams eigenfunction approach. We had looked at what is the stress function form, and we have looked at what are the boundary conditions. We are not talking anything about what happens at infinity. We are only saying the crack faces are free. At infinity, you only say you have smoothly varying loading situation. And we had a long discussion and then finally obtained what are the eigenvalues. The eigenvalues have to be positive integers. We have also looked at the reasoning for it. Then we also commented among the 4 coefficients, interrelationships exist. There is an interrelationship between C3 and C1 and C4 and C2. We have looked at this for n equal to 1, 3, 5 and so on. We have also looked at it for n equal to 2, 4, 6. So now we are ready to write the stress function completely. Whatever the exercise that we did in the last class has helped us to write what is the stress function for this class of problem, and the stress function turns out to be like this. Mind you, in this class you have to write long expressions, there is no other go. So what I would do is I would also read it for you. The stress function phi has two summation series, one series when n equal to 1, 3, 5 odd numbers, another series when n are even numbers 2, 4, 6 etc. And the first series is like this, r power 1 plus n by 2 multiplied by C1n cos n minus 2 divided by 2 theta minus n minus 2 by n plus 2 cos n plus 2 by 2 theta plus C2n multiplied by sin n minus 2 by 2 theta minus sin n plus 2 by 2 theta. And the second series for n equal to 2, 4, 6 etc. you have r power 1 plus n by 2 multiplied by C1n cos n minus 2 divided by 2 theta minus cos n plus 2 by 2 theta. In fact, while reading I am not reading the brackets, by looking at the figure and the slide it is possible for you to put the brackets appropriately, plus C2n sin n minus 2 by 2 theta minus n minus 2 divided by n plus 2 sin n plus 2 by 2 theta. And what you have when you have a stress function in this form, you have a symmetric as well as an antisymmetric part. This we had not seen in the Westergaard stress function approach. We solved mode 1 problem separately, we solved mode 2 problem separately, and what you find here, you get the stress function in the form of a series, that is observation number 1. Observation number 2 is you have cosine terms as well as sine terms. I could group all the cosine terms involving C1n. This is symmetric and this is the stress function for the mode 1 loading. And you have a antisymmetric part, you have a sine function. Whatever the terms associated with C2n will address crack problems involving mode 2. So, in one go you get the solution for mode 1 as well as mode 2 in the case of Williams eigenfunction approach. This is observation number 2. And we will also have one more observation. See, if you look at the second term in the mode 1 loading, that is nothing but n equal to 2, if you write this expression, I will have this as r squared C12 cos 0, so that it will become 1 minus cos 2 theta. So, that would be the second term of the stress function. Mind you, you are looking at the stress function, and we have also had some discussion what are the forms of stress function. So, if you look at the form of this stress function r squared multiplied by 1 minus cos 2 theta, it actually represents a uniaxial stress field in the x direction. This was also observed by Williams when he reported the solution in 1957. If he had said, when you are analyzing crack problems, take as many terms in the series as possible for modeling, people would have looked at his solution differently and also used it differently. But what he said was, suppose you have a uniaxial loading situation when the vertical edge is free, he made a comment that the constant C12 should become 0 to satisfy the boundary condition, which is a very unfortunate statement. If he had not made that statement, people would have realized the role of second term in the series right then. Just because he had made that statement and people are focusing more on what happens at the crack tip, they were concentrating only on the singular field. What way now you will have to look at is, when I have a stress function in series form, For any given problem, depending on the kind of situation, you may have to evaluate the coefficients. As you take as many coefficients as possible, that would satisfy the far field boundary condition. When you have a free edge, it is not only C12 should go to 0. Combination of several coefficients can satisfy that boundary condition. That is how any general solution has to be looked at. Just because people looked at circular hole in a tension strip, elliptical hole in a tension strip, for crack problems also they were focusing on uniaxial loading, whereas in the Westergaard solution the basic approach was on biaxial stress field, it is not for uniaxial stress field. But after looking at all that, we have now an understanding that when you say Z0 is very close to 0, very small compared to the crack length, you are essentially focusing on a zone very close to the crack tip. So what really happens is, it is only the crack face displacements that is important in the case of fracture mechanics, whether it is a opening mode, in plane shear mode or out of plane shear mode, you have to look at only on the crack face displacements. The far field loading is secondary. So once you take up a multi-parameter solution, from now on we will have to say take as many terms that would satisfy your problem under consideration. Once you know phi, what is the next step? You can easily find out the stress field. And in the case of polar coordinates, once you have sigma phi is known, sigma r is defined as 1 by r dou phi by dou r plus 1 by r squared dou squared phi by dou theta squared. Then sigma theta theta equal to dou squared phi by dou r squared, and tau r theta equal to minus dou by dou r of 1 by r dou phi by dou theta. In fact, I would like you to try out at least sigma theta theta. You have the function phi, you do not take many terms, just take the first term and you will only worry about C11. You have the Airy stress function given. For C11, you find out sigma theta theta, that is the simplest one to find out. And in this case, what way you are going to get? You are going to get polar components. You are actually looking at sigma r, sigma theta, tau r theta. They would also be expressed in terms of r and theta coordinates. So the expressions would be different than what you had seen in Westergaard solution. So do not come to a wrong conclusion. I have expressions for the stress field, they are different from Westergaard. They have to be different because here you are looking at sigma r, sigma theta and tau r theta. When you transform this to Cartesian coordinates, the solution will be identical. Because this is again, I have been emphasizing it, in the case of Westergaard solution, when I have Cartesian stress components expressed in terms of r and theta. So please work it out, so that way this will help you to follow the class. And what we will do is, we will see the singular solution as well as multi-parameter solution. You have to work it out. Anyway, for the benefit of those who have already done this, we get the very near tip stress field equations in polar coordinates. And I have also written the expression in a fashion that I have a term 1, I have put plus some dots I have put. This indicates that you have higher order terms, and you have sigma r, sigma theta, tau r theta. The common factor that is taken out is k1 divided by 4 root of 2 pi r, and you have a function of theta. For sigma r, the function is 5 cos theta by 2 minus cos 3 theta by 2, and for sigma theta it is 3 cos theta by 2 plus cos 3 theta by 2. and you have sin theta by 2 plus sin 3 theta by 2 for tau r theta. See, we had made some observation after we looked at Westergaard's singular solution. We have looked at the stress field. We have also looked at how sigma x and sigma y varies. And what is that we noted at the crack tip? We noted at the crack tip sigma x is equal to sigma y, and you do not have a shear stress at the crack tip, it is 0. So, sigma x and sigma y are principal stresses. So, when two quantities are equal, every direction is a principal stress direction. So, what does it imply? What way you should have sigma r and sigma theta at the crack tip? They will also have to be equal. Are we having it as equal? We will have a look at the solution. So, at the crack tip you will say theta equal to 0. So, when I say theta equal to 0, I have this as 5 minus 1. So, this is 4, and this will be 3 plus 1. So, this is also 4, and your tau r theta is going to be 0. So, now you find that principal stresses are equal, and what is the kind of stress field is this? Particularly when you are looking at a plane strain situation, that is interior to the object, you will also have a sigma z component, and what people have noted is you have a triaxial loading situation, and you have hydrostatic type of loading. From your understanding of solid mechanics, what you find when you have hydrostatic type of loading, you can't have plastic flow. So, the material has to follow some other kind of failure mechanism. So, this is the reason Williams also attributed while discussing his results, because you have hydrostatic type of loading near the crack tip. In view of it, there may not be possibility of plastic flow, the material fails by cleavage fracture. It is a very important observation that you have hydrostatic type of loading, the stresses are equal. This is a very important observation, and later on we will also look at what is known as triaxiality constraint. So, all that we will look at. So, the stress field is not innocent. So, you find when r goes to 0, stresses become singular, and this is what we have obtained for mode 1 situation. On similar lines, you could also obtain the stress field for mode 2, and mode 2 it is like this. So, I have sigma r, sigma theta and tau r theta, which is given as k2 divided by 4 root of 2 pi r multiplied by minus 5 sin theta by 2 plus 3 sin theta by 2. This is for sigma r, and for sigma theta the function is minus 3 sin theta by 2 minus sin 3 theta by 2, and you have for tau r theta cos theta by 2 plus 3 cos 3 theta by 2. Even while writing it, I write it in such a fashion that you have higher order terms. See, the higher order terms are explicit when you follow the Williams function approach. When you do the Williams eigenfunction approach, the stress function is in a series form, and you get several terms in the series. You are looking only at the first term, which happens to be the singular term. And if you really look at experimental literature, when people have used method of caustics, they have directly taken up the stress field in polar coordinates. When you go and look at any paper on caustics, these equations were found to be convenient to handle. Now, what we will do is we will not stop at the first term, we would see a multi-parameter solution. We will not see several terms, we will see a 6-term solution. The letters are very small. What I would do is, even if I magnify, you may not be able to see the complete set of stress field. So, I would read them, and my reading speed and your writing speed should match. If there are any corrections, please advise me to follow it slow. And these equations are very important. The reason why I am saying this is, you will not find them in books. So, at the end of the course, you should have rich collection of important results. So, you start writing with me. For sigma r, I have 6 terms, and it starts at, the first term is r power minus 1 by half multiplied by C11, and you have a set of terms 5 by 4 cos theta by 2 minus 1 by 4 cos 3 theta by 2 plus 4 C12 cos squared theta plus r power half 3 C13 multiplied by 3 by 4 cos theta by 2 plus 1 by 4 cos phi theta by 2 plus 2 r C14 multiplied by cos theta plus 3 cos 3 theta plus r power 3 by 2 C15 multiplied by 5 by 4 cos 3 theta by 2 plus 15 by 4 cos 7 theta by 2 plus r squared C16 multiplied by 12 cos 4 theta. So, what you have here is, look at the second term. The second term is a constant term in the sigma r also. So, you have this additional term which was misunderstood earlier, and you have to take this into account. And you have the expression for sigma theta, that turns out to be r power minus half 3 by 4 C11 cos theta by 2 plus 1 by 3 cos 3 theta by 2. The second term is 4 C12 sin squared theta plus r power half 15 by 4 C13 multiplied by cos theta by 2 minus 1 by 5 cos phi theta by 2. The next term is 6 r C14 cos theta minus cos 3 theta plus 35 by 4 r power 3 by 2 C15 multiplied by cos 3 theta by 2 minus 3 by 7 cos 7 theta by 2 plus 12 r squared C16 cos 2 theta minus cos 4 theta. So, this is for sigma theta. Then you go for tau r theta. Tau r theta is r power minus half multiplied by 1 by 2 C11 multiplied by 1 by 2 sin theta by 2 plus 1 by 2 sin 3 theta by 2 minus 2 C12 sin 2 theta plus r power half 3 by 2 C13 multiplied by 1 by 2 sin theta by 2 minus half sin phi theta by 2 plus 2 r C14 sin theta minus 3 sin 3 theta plus r power 3 by 2 5 by 2 multiplied by C15, which is multiplied by 3 by 2 sin 3 theta by 2 minus 3 by 2 sin 7 theta by 2, and the last term is 3 r squared C16 2 sin 2 theta minus 4 sin 4 theta. The expressions are very long. This is a 6 term solution for what? This is for mode 1 loading, because Williams gives you mode 1 as well as mode 2. So, I am going to have another set of expressions for mode 2. Why I want you to write is, we would see another elegant representation. You would appreciate that representation is elegant only when we write down this complex expressions. So, that exercise also will help you to do that. So, now I have for mode 2, for all the mode 2 terms, you have the coefficient starting as C2. So, for sigma r it is minus r power minus 1 by 2 multiplied by C21 5 by 4 sin theta by 2 minus 3 by 4 sin 3 theta by 2 plus r power half 3 C23 multiplied by 3 by 4 sin theta by 2 plus 5 by 4 sin 5 theta by 2. Mind you, the second term is 0 here. I had already mentioned, even in the case of generalized Westergaard equations, the singular solution for mode 2 reasonably matches with experimentally observed fringes. The role of second term was not influenced, and I mentioned that second term is 0. Even when you consider a series solution for mode 2, the sigma x stress component, the second term is 0. A similar thing is also observed in the polar components. Here you have to be very careful, you have to transform the polar whatever the polar components to Cartesian components, and you have the third term is 2r c 24 sin theta plus sin 3 theta plus r power 3 by 2 c 25 5 by 4 sin 3 theta by 2 plus 35 by 4 sin 7 theta by 2 plus r squared c 26 6 sin 4 theta. And for sigma theta, you have this as minus r power minus half multiplied by 3 by 4 c 21 sin theta by 2 plus sin 3 theta by 2 plus r power half 15 by 4 c 23 sin theta by 2 minus sin 5 theta by 2 plus 6 r c 24 sin theta minus 1 by 3 sin 3 theta plus 35 by 4 r power 3 by 2 c 25 sin 3 theta by 2 minus sin 7 theta by 2. And the last term is plus 12 r squared c 26 sin 2 theta minus half sin 4 theta, and you have the shear stress term r power minus half 1 by 2 c 21 multiplied by 1 by 2 cos theta by 2 plus 3 by 2 cos 3 theta by 2 minus r power half 3 by 2 c 23 multiplied by 1 by 2 cos theta by 2 minus 5 by 2 cos 5 theta by 2. And I have this next term as minus 2r c 24 cos theta minus cos 3 theta minus r power 3 by 2 5 by 2 C23 multiplied by 3 by 2 cos 3 theta by 2 minus 7 by 2 cos 7 theta by 2, and the last term is minus 3 r squared C26 2 cos 2 theta minus 2 cos 4 theta. So, now you have a 6 term solution in polar coordinates given by Williams eigenfunction approach. This is very clumsy. If you have this kind of a form, the solution would not have become popular. There was a very nice work done by Atluri and Kobayashi. They simplified and represented all the multi-parameter stress field equations in a very elegant fashion. We will look at that solution shortly. Before we go into that, let us also look at what is the kind of stress function for the generalized mode 2 Westergaard stress function that we have to look at. We have only looked at length what to do for mode 1 situation. We have not looked at how the area stress function changes in the case of mode 2. We will have a look at that. I am just going to give you the stress function and the stress field. I will not get into the mathematical details, and the area stress function takes this form: imaginary part of y2 double bar. Since we are discussing mode 2, I have put a subscript 2. When we discussed mode 1 situation, we simply gave capital Z and capital Y. We did not give the subscript 1 there. Since we are discussing specifically the mode 2 situation, we are putting the subscript 2 here. So, I have stress function phi as imaginary part of y2 double bar minus y real part of y2 bar plus real part of z2 bar. If you recall, the singular solution which we obtained had only this minus y real part of z2 bar. These two terms are additional. Once area stress function is defined, it is possible for you to get the stress field, and I would write the stress field in the form of stress functions only. I have sigma x, sigma y, tau xy, and sigma x is given as imaginary part of y2 plus y multiplied by real part of y2 prime plus real part of z2 prime plus 2 imaginary part of z2, and you have sigma y is given as imaginary part of y2 minus y multiplied by real part of y2 prime plus real part of z2 prime, and the shear stress tau xy is given as minus y times imaginary part of y2 prime plus imaginary part of z2 prime plus real part of z2. So, now you have the generalized mode 2 Westergaard solution. So, if you look at the form of the stress function z2 and y2, you can construct a series solution, and what is mentioned is the stress functions y2 and z2 have similar form as their mode 1 counterparts. And what are the mode 1 counterparts? Now, mode 1 counterparts, you had this function z and y given as a series solution. So, you need to go for a series solution like this, and you have to ensure that Z2, real part of Z2 is 0 on the crack faces to satisfy the boundary condition there. Similar to mode 1 situation, here also imaginary part of y2 should be 0 on y equal to 0. And we also look at the kind of stress fields that we saw for the mode 1. Something similar to this I would like you to work it out for mode 2, and the expressions are like this. You also wrote down these expressions, and I said they are very clumsy. We have also written down Williams eigen solution results for 6 terms. They were also very difficult to write. Now we will go and see the solution given by Atluri and Kobayashi, and they are the most elegant form of stress field expression, and you have to write this down very carefully. I have sigma x, sigma y, tau x y. So these expressions give only Cartesian stress components, and this is given as summation of 2 series. The first series involving the coefficient capital A1 n, the second series involves capital A 2 n. So the first series is meant for mode 1 loading, whereas the second term in the series is meant for mode 2 loading, and n varies from 1 to infinity. I have n by 2 a 1 n r power n minus 2 divided by 2, and for sigma x I have this as 2 plus minus 1 power n plus n by 2 cos n by 2 minus 1 theta minus n by 2 minus 1 multiplied by cos n by 2 minus 3 theta, and for the sigma y stress term it is 2 minus 1 whole power n minus n by 2 multiplied by cos n by 2 minus 1 theta plus n by 2 minus 1 multiplied by cos n by 2 minus 3 theta, and for shear stress it is minus of minus 1 power n plus n by 2 multiplied by sin n by 2 minus 1 theta plus n by 2 minus 1 sin n by 2 minus 3 theta. See, you will have to notice one thing. I have the mode 1 stress field as well as mode 2 stress field in terms of generic expression. When I change n, I would get the second term, third term, fourth term and so on. I can easily computerize the set of equations. That is advantage number 1. And another aspect is it is easy for computerization, and what you will have to look at is this solution was reported in handbook of experimental mechanics first, and it had 1 or 2 small typographical errors. Even a change in minus or plus sign or a sign to cos can cause havoc. So these expressions are edited, they are as accurate as possible, and these are used to reconstruct a fringe pattern for complex problem situation, which we would also see in this class. So take some time in writing these expressions as accurately as possible, because these equations are verified free of any typographical errors. For mode 2, this is minus of summation n equal to 1 to infinity n by 2 a 2 n r power n minus 2 divided by 2, and for sigma x it is 2 minus 1 power n plus n by 2 multiplied by sin n by 2 minus 1 theta minus n by 2 minus 1 sin n by 2 minus 3 theta, and for sigma y it is 2 plus minus 1 power n minus 1 by 2 n by 2 multiplied by sin n by 2 minus 1 theta plus n by 2 minus 1 sin n by 2 minus 3 theta minus of minus 1 power n minus n by 2 cos n by 2 minus 1 theta minus n by 2 minus 1 multiplied by cos n by 2 minus 3 multiplied by theta. And you can again look at the expression, ensure that no sign change or sin or cos change is done in your expression. And how the coefficients are defined? See, we are interested in one or two coefficients, because we want to find out what is k1 and k2, and the second term in the sigma x stress field for mode 1 situation we label it as sigma naught x. How the coefficients are related to the quantities that we already know. So, that is given here. I have A11 is given as k1 by root of 2 pi, please write this down, and as I mentioned earlier, the terms involving A1 corresponds to mode 1 loading, the terms involving A2 corresponds to mode 2 loading, and A21 is related to minus k2 divided by root of 2 pi. This minus and minus becomes plus, that is how it is written. So, I can find out, if I know the coefficients as part of the solution, I can find out what is k2 and k1, and the second term in the sigma x series is related to sigma naught x in this fashion, 4a12 equal to minus sigma naught x, and we would see the utility of these expressions. Showing such long expression is not going to enthuse you. We just make an observation of this animation, and what you see on the right side is the experimentally obtained fringe pattern. I have a crack, I have forward tilted loops as well as frontal loops, and on the left side you have the solution obtained from experiments, which is done by a over deterministic least square methodology, and the number of terms in the series solution are incrementally increased. You would notice it is for 4 parameters, 5 parameters, 6 parameters, 7 parameters and 8 parameters, and you can also notice that the values of k1 and sigma naught x change as a function of number of parameters. Now, what I want you to look at is, I will magnify this picture. You see red dots. These red dots are the points selected from the experiment. So, that is the input to your algorithm. If time permits, maybe towards the end of the course we will look at the algorithm, otherwise you can look at the reference and know what the algorithm is. So, the idea is, these are all the experimentally obtained points, and from these data you evaluate the series coefficients. Using the series coefficients, replot the fringe pattern, because you know how to calculate the maximum shear stress, and you also know what is the material stress fringe value for the given problem. Using that, it is possible to reconstruct the fringe pattern. The idea is, the reconstructed fringe pattern should closely match the experimentally obtained data. So, what I want you to make an observation is, as the number of terms changes, how the geometric features of the fringe change, and as the number of terms are increased, you will find the geometric fringe pattern match with the experimental data. Simultaneously, also notice the variation in the values of k1 and sigma naught x. These are two pertinent parameters in the case of a mode 1 situation. So, I will repeat the animation. So, it is going for 5 parameters, At 6 parameters, you know, the contours match. You find 7 and 8, there is hardly any change. So, beyond 6 parameters, whatever the complicated fringe contours which you observed in an experiment is very nicely captured from your post processed results, and the final value of K1 and sigma naught x are given here. K1 is 0.656 MPa root meter and sigma naught x is 2.919 MPa, and we look at what happens in the case of a 2 parameter solution. We start from a 2 parameter solution, we do not start from Westergaard's singular solution. We said even for short cracks I cannot rely on Westergaard's singular solution, I have to have minimum of 2 parameters. So, when I have minimum of 2 parameters, what do I observe? I only get forward tilted loops and the fringes are not matching with the experimental data. You see red dots several places, and what is the value of K? K is only 0.445, whereas sigma naught x is quite high. See, if I take a 2 term solution and if my K is same as what I am going to get with a 6 term solution, I do not have to worry. But what you find here is a 6 term solution gives K as 0.656, here it is for 8 term solution, which is higher than the K for 2 term solution. So, which definitely says that you need to go for higher order terms, otherwise K1 evaluation is erroneous. Not only this, we have seen in sufficient discussion that people have looked at the second term in various ways, and we have been saying you should get the second term as part of your solution. Whatever the solution gives, you may have to take it. If I take a 2 term solution, I get sigma naught x is 4.436, but it does not remain constant. 2 term solution is not sufficient to model this situation. So, interpreting sigma naught x equivalent to the far field stress field, that kind of discussions are not completely correct. Let us look at what happens to a 3 term solution. So, for 3 parameter, K changes, sigma naught x changes, and you find the frontal loops are not at all matched. You go to 4 terms, there is semblance of formation of frontal loops, and you find K is steadily increasing and sigma naught x is diminishing. 5 terms it is slightly better, and if I have 6 terms, all the fringe features are captured, and beyond 6 terms what you find? The solution stabilizes. I know this is done by a non-linear least squares analysis. The coefficients A11, A12, A13, A14, A15, A16, they were calculated based on the experimental data. It is a very sophisticated algorithm. Based on that you replot and you find for this problem at least 6 parameters are required to model. And when you are having a least squares approach, there is no guarantee that your final solution is correct. Here, in order to ensure that my final solution is matching with the experiment, the fringe patterns are reconstructed and you ensure that we have converged to a proper minimum, so that the solution is indeed representative of the stress field. Now, you find there is quite a variation in the geometric features. We will also have a look at what happens in the case of holography. You look at what way the fringes change for 2 parameters, 3 parameters, 4 parameters, 5 parameters and 6 parameters, and what do you find? You do not find a great change in the geometry. See, we have been discussing for the crack problem, we wanted tau xy to be 0 on the crack axis. Westergaard solution turned out a surprise that tau maximum is also 0, which is incidental, we did not want it, whereas the experiment shows there is a variation of maximum shear stress along the crack axis, which is beautifully captured when you go for a system solution. So, the final understanding is it is desirable that you go for multi-parameter stress field solutions and evaluate the coefficients based on the stress field, and that is how we will have to look at the equations in fracture mechanics, and we will also see more than one example in the next class. We would also see the multi-parameter displacement field equation, and you have seen Westergaard, generalized Westergaard, then Williams eigenfunction, then Atturi Kobayashi. They can't be different. Uniqueness theorem says you have to have one solution for one problem. So, we would also look at the identity between the coefficients. In fact, the next class I would like you to sketch some of these fringe patterns. You also need to have these fringe patterns as part of your notes. So, in this class what we had looked at was, we had looked at multi-parameter stress field equations. Although we wanted to see displacement field, we will postpone it to the next class. Lot of writing you had to do, and these equations are very important and you may not find them in books. So, these equations will come in handy when you need them. Thank you.